So therefore this S satisfies all these three properties, and we call such a class of sets as Semiring. So if any class of sets has these three properties, then that class of sets is said to be as Semiring. So now we properly define this Semiring in a more abstract way. So let's define this Semiring. What's Semiring actually? What is Semiring? Let x be not equal to 5. Let x be not equal to 5. It's any non-empty set. And let S be a family of subsets of x. Subsets of x. So in this earlier example, x has x was the set of real numbers, so it was the real line in that case, and the S, it was the family of semi-closed intervals in previous example. So here x is a non-empty set, and S be a family of subsets of x satisfying following properties. Satisfying following properties. First property, phi should be the member of S. Phi should be the member of S. Second property, if A1 and A2 be any two members of S, then it should imply their intersection should be the member of S. Should be the member of S. Third property is, if A1 and A2 are any two members of S, then the difference, set difference, A1 minus A2 should be equal to the finite disjoint union of members of S. Where these CIs, they are all members of S and they are also pairwise disjoint for I not equal to G. X is a non-empty set, S is a family of subsets of X satisfying these properties, then we say S is a Semiring. Then we say that class of sets S is a Semiring. So what is Semiring actually? It's a class of subsets of certain non-empty set X satisfying these three properties. Phi should be the member of S. It should be closer with respect to intersection, means if we choose any two members of S, then their intersection must be the member of S. And third property, if we choose any two members of S, then their set difference must be equal to the finite disjoint union of members of S. That's the definition of Semiring. An example, we have already discussed the example of Semiring. The class of semi-closed intervals is a Semiring. That's the example of Semiring. Next, we discuss certain properties of Semiring. First of all, we define sigma set. What do we mean by sigma set? Sigma set. Sigma means countable. Sigma stands for countable actually. Sigma. So, what's sigma set in Semiring? Let's define this sigma set. Let X be a non-empty set and S be a Semiring. S be a Semiring on X. S be a Semiring on X. Semiring on X means S is a class of subsets of X satisfying those three properties. It's a semiring on X. Now let A be any subset of X. Is any subset of X. Then we say A's sigma set with respect to this semiring S. It depends upon the semiring actually. Then we say A is a sigma set with respect to the semiring S if there exists a disjoint sequence An of members of S. The members of this sequence are elements of S. Actually, they are members of S. Sequence An of members of S. That means each An belongs to S. So each An is a subset of X, but it's also the member of S. And they are also disjoint. So a subset A is said to be a sigma set with respect to S, with respect to this semiring S, if there exists a disjoint sequence An in semiring S such that A is equal to union An runs from 1 to infinity. This is the definition of sigma set. So in case this A is finite, disjoint union of members of S, then that A is always a sigma set. So in case A is equal to union AK, K runs from 1 to N, finite, they are finite, where these AKs, they belong to S and they are also pairwise disjoint for I not equal to J, 1 lesser equal to I comma J lesser equal to N lesser equal to N. So in case A is finite disjoint union of members of S, then we show that this A is also a sigma set. It's also a countable disjoint union of members of S. Then this A can be written as union A K, K runs from 1 to infinity, where this An plus 1 equal to An plus 2 equal to so on equal to 5. If A is equal to A1 union A2 union up to union An, then A is equal to A1 union A2 union up to union An, then union An plus 1 union An plus 2, where those sets An plus 1, An plus 2, An plus 3, they are all 5 sets. So whenever A is finite union, we can express this A as a countable union by inserting these null sets. And clearly this A is now sigma set because it is a countable union of members of S, and they are all pairwise disjoint because AKs are pairwise disjoint, and we inserted here null sets. So null sets are also pairwise disjoint. So therefore, whenever A is a finite union of disjoint sets, then A is also always a sigma set. That's the definition of sigma set. Now, one can easily verify that any member of semiring is a sigma set. So if S is a semiring, if S is a semiring on some non-empty set X, and A is a member of S, then A is always a sigma set. How it is a sigma set? How it is sigma set? Because we can write A as A union phi up to infinity. So this A can be written as countable union of disjoint members of S because they are all members of S. A is a member of S, phi is a member of S, they are all members of S, and they are also pairwise disjoint. Therefore, is a sigma set. So every member of a semiring is a sigma set with respect to that semiring S. So also if S is a semiring, if S is a semiring and A comma B belongs to S, then by definition of semiring, A minus B, the set difference of two members of a semiring, is equal to the finite disjoint union of members of S. It's equal to C1, C2 union up to union Cn, while these Ci's, they are members of S and they are also pairwise disjoint. So it means that this set difference is actually a sigma set, because whenever a set can be written as finite disjoint union of members of S, then such sets, those sets are always sigma sets. So therefore A minus B is a sigma set. It's always a sigma set. So that's very simple. We have already discussed it. How a set which is a finitely disjoint union of members of S is a sigma set, and here this set difference, it is a finite disjoint union of members of S. Therefore, that set difference is always a sigma set. So the condition is that these two members should be the members of S. That's the condition here. So next we have a theorem. That's the first theorem of this course. Theorem number 1. So here I will write it's lecture 1. Lecture 1. Theorem 1. So what's the statement of theorem? For a semiring S, the following hold. For a semiring S, the following hold. For a semiring S, the following hold. The first property is if A is a member of S and A1, A2 up to An, they are also members of S. They are also members of S. Okay, A is a member of S, and these N sets, they are also members of S. Then this A minus union AI, I runs from 1 to N. This set difference A minus union can be written as a finite disjoint union of members of S. And second property that we have to prove, for any sequence, of sets in S, union A and N runs from 1 to infinity is a sigma set. Is a sigma set. And third and last property that we have to prove, countable unions and finite intersections of sigma sets is again sigma sets are again sigma sets. So we prove these three properties for a semiring S. If S is a semiring and A is a member of S, and if I choose any n members of S, then A minus union AI runs from 1 to n can be written as a finite disjoint union of members of S. And for any sequence an in S, the union an runs from 1 to infinity is a sigma set. And third, the countable unions and finite intersections of sigma sets are again sigma sets. So let's prove a first property. To prove a first property, we use induction on n, on the number of sets. So let's prove this property, first property. First property. So first property. What's first property? We have a member of S here, and these are n members of S, A1, A2, so on up to n there. We show that A minus union AI runs from 1 to n is a finite disjoint union of members of S. So to prove this result, we use induction on n, the number of sets. We use induction on n. For n equal to 1, we have to show that A minus A1, because here n is 1, I runs from 1 to 1, so it is just A1. This union is A1. For n equal to 1, result follows from the definition of semiring, because at that moment A is a member of semiring, A1 is also a member of semiring, and by definition set difference of any two members of semiring can be written as finite disjoint union of members of S. So then A minus A1 is a finite disjoint union of members of S by definition by definition of semiring. So it is very simple. It follows from the definition of semiring. And now we assume that result holds for, say, n equal to k. So assume result holds for n equal to k. Assume result holds for n equal to k, that is if A belongs to S and A1, A2, so on up to AK, they are also members of S, then A minus union AI runs from 1 to K is a finite disjoint union of members of S, is a finite disjoint union of members of S. So assume result holds for n equal to k means this thing holds. That is, if A is a member of S and we have k members of S, then that set difference can be written as finite disjoint union of members of S. So we prove that result also holds for n equal to k plus 1. That is, we show that for any set A in S and for any k plus 1 sets A1, A2, AK plus 1 in S, we show that A minus union AI, I runs from 1 to k plus 1, is a finite disjoint union of members of S. So we show that result also holds for k equal to n equal to k plus 1. We show that result holds for Unequal to k plus 1. So for this we choose let A belongs to S and A1, A2, so on up to AK plus 1 or K plus 1 members of S. Then by induction hypothesis, then we have to find this actually. A minus union AI, I runs from 1 to K plus 1. We show that this set difference can be written as finite disjoint union of members of S. It's equal to A minus union AI, I runs from 1 to K, then minus A K plus 1. So you can easily verify this. That set difference is equal to this set difference. They are same actually. And this one, since result is true for n equal to k, so therefore A minus union I runs from 1 to k, AI can be written as finite disjoint union of members of S. So it's equal to B1 union B2 union so on union say Bm minus AK plus 1, where what are these BIs? Where these BIs, they are the members of S and they are also pairwise disjoint. It's this follows by inductive hypothesis. Inductive hypothesis. Okay. So here, now here it's equal to, it's B1 minus AK plus 1, this is that difference, B1 minus AK plus 1 union B2 minus AK plus 1 union up to Bm minus AK plus 1. Next, it's B1, it's a member of S. AK plus 1, it's also a member of S. Therefore, B1 minus AK plus 1 can be written as finite disjoint union of members of S. Here, B2, it's a member of S. AK plus 1, it's also a member of S. Therefore, B2 minus AK plus 1 can be written as finite disjoint union of members of S. And finally,